Hello students, let us continue the session on triangles. In the previous session, we had stopped at exercise 6.2 first question. We shall continue from the second question onwards. So the second question is, E and F are the points on the sides PQ and PR respectively of a triangle PQR. For each of the following cases, state whether EF is parallel to QR. The first one is PE equal to 3.9 cm, EQ equal to 3 cm, PF equal to 3.6 cm, FR equal to 2.4 cm. Suppose if I consider the triangle as PQR, let this point be F and this point be E. PE is given as 3.9 cm, EQ is 3 cm, PF is 3.6 cm, FR is 2.4 cm. We have learned in our previous session that if the ratio of the sides PE by EQ is equal to PF by FR, then we can say that EF is parallel to QR by the converse of Tayl's theorem. If I find the ratio now, what is PE upon EQ? PE upon EQ is 3.9 upon 3. We get it as 1.3. PF upon FR is 3.6 upon 2.4. This is nothing but 36 by 24. 4 9 times, 4 6 times, 3 3 times, 3 2 times. We get it as 1.5. Here PE upon EQ is not equal to PF upon FR. This implies EF is not parallel to QR. Let's do the second one. If I consider PE upon EQ, this will be 4 upon 4.5. If I multiply by 2, it becomes 8 by 9. And PF upon RF is 8 by 9. Here, PE upon EQ is equal to PF upon RF. This implies EF is parallel to QR by converse of Tayl's theorem. Let us do the third one. In the third one, they have given the length of PQ and the length of PR, the length of PE and PF. So better I draw a diagram in which the length of PQ is given 1.28, the length of PR is 2.56, the length of PE is 0.18, and the length of PF is 0.36. If I consider the ratio PE upon PQ, this will be 0.18 divided by 1.28. I can shift the decimals, it becomes 18 by 128 to 9 times to 64 times. So it is 9 upon 64. And I consider PF upon PR, this will be 0.36 divided by 2.56. which is 36 upon 256. 4 9 times, 4 64 times, we get the same ratio here. P upon PQ is equal to PF upon PR. This concept we had learned as a corollary. Therefore, since the ratio of the sides are equal, we get EF parallel to QR by converse of Tayl's theorem. Or else what you can do is you can subtract both from 1 minus. If you do 1 minus P upon PQ will be, sorry, you can take the reciprocal, not this. If you take the reciprocal, it becomes PQ upon PE equal to PR upon PF. Then you subtract 1 from both the sides, you'll be getting PQ minus PE by PE is equal to PR minus PF by PF. PQ minus PE is nothing but EQ. So EQ upon PE will be equal to FR upon PF. We get the ratio of the sides equal. So instead of doing all this, directly I can consider it as a corollary and I can mention the converse of Tayl's theorem. We get EF parallel to QR. Question number 3. In figure 6.18, if LM is parallel to CB, LN is parallel to CD, prove that AM by AB equal to AN by AD. Since they have given that LM is parallel to CB, I can consider the Tayl's theorem. I can write AM upon AB equal to AL upon AC. I'll name this as equation 1. This is from Tayl's theorem. So I'll write in the beginning that from Tayl's theorem we have LM parallel to CB, and they also given that LN is parallel to CD. Now I'll consider this triangle. In this triangle we have AL upon AC equal to AN upon AD. This is equation 2. From equation 1 and 2, we get AM upon AB equal to AN upon AD, because AL upon AC is common in both the equations. Let us consider question number 4. In figure 6.19, DE is parallel to AC and DF is parallel to AE. Prove that BF upon FE equal to BE upon EC. Now I'll consider separately the triangles. I'll consider in triangle ABC. We have DE parallel to AC. This implies from Tayl's theorem BD upon DA equal to BE upon EC. I'll name this as 1. This is from Tayl's theorem. Now I'll consider the triangle ABC in which DF is taken parallel to AE. If DF is parallel to AE, I get BD upon AD equal to BF upon EC. BF upon. So from 1 and 2, we get BE upon EC equal to BF upon FE. Hence we have proved it. BF upon FE equal to BE upon EC. Question number 5. In figure 6.2, DE is parallel to OQ, DF is parallel to OR. Show that EF is parallel to QR. Let me consider DE parallel to OQ in triangle POQ. So in triangle POQ, since DE is parallel to OQ, I get PE upon EQ equal to PD upon DO. This is from Tayl's theorem. Let me name this as equation 1. Now I'll change the color. Now I will consider DF parallel to OR in triangle POR. So in triangle POR, we have given DF parallel to OR. So from Tayl's theorem, we have PF upon EFR equal to PD upon DO. This is again from Tayl's theorem. Let me call this as equation 2. From equation 1 and 2, we get PE upon EQ equal to PF upon FR. Now in triangle PQR, since PE upon EQ is equal to PF upon FR, we get EF is parallel to QR. This is from Converse of Tayl's theorem. Question number 6. In the figure 6.21, A, B and C are the points on OP, OQ and OR respectively. AC is parallel to PR. Show that BC is parallel to QR. It is given that in triangle POQ, we have AB parallel to PQ. So from Thay's theorem OA upon AP is equal to OB upon BQ. I have taken AB parallel to PQ in this triangle. Now, in the triangle POR, if I consider the triangle POR, since AC is given parallel to PR, in triangle POR, since AC is parallel to PR, we have OA upon AP equal to OC upon CR. Let me call this as equation 1 and this as equation 2. From equation 1 and 2, we have OB upon BQ equal to OC upon CR. Therefore, in triangle OQR, since OB by BQ is equal to OC by CR, this implies BC is parallel to QR from converse of Tayl's theorem. So most of the questions are related to converse of Tayl's theorem. Question number 7. Using theorem 6.1, this theorem 6.1 is nothing but Tayl's theorem. So using Tayl's theorem, prove that a line drawn through the midpoint of one side of a triangle parallel to another side bisects the third side. You need to recall that we have proved it in class 9th. We had called it as a midpoint theorem. This concept was there in class 9th. Let us use Tayl's theorem and prove midpoint theorem. For that, I would like to consider a triangle such that P is the midpoint of the side AB. P is the midpoint of the side AB. So these two sides are equal. If a line is drawn parallel to a side of a triangle, it bisects the other side. Let me call this as point as Q. So let PQ is a line through the midpoint of AB parallel to BC intersects AC at Q. That is, PQ is parallel to BC. In triangle ABC, since PQ is parallel to BC, we have AP upon PB equal to AQ upon QC. This is from Tayl's theorem. As it is mentioned here, AP and PB, they will be equal. Since P is the midpoint, we get the ratio as 1. So 1 will be equal to AQ by QC. On cross multiplication, we get AQ equal to QC. What if AQ equal to QC? we get the point Q as the midpoint of AC. Hence, we have proved the midpoint theorem. Let us solve one more question. This will be the last question for today's session using theorem 6.2. The theorem 6.2 is converse of Tayl's theorem. So using the converse of Tayl's theorem, we need to prove that the line joining the midpoints of any two sides of the triangle is parallel to the third side. This concept also we have learned in class 9th. This concept is converse of midpoint theorem. So using the Tayl's theorem, we can prove midpoint theorem, and using the converse of Tayl's theorem, we can prove the converse of midpoint theorem. Again, I'll consider the same triangle ABC, and I'll consider point P and Q. So let PQ is a line which passes through the midpoints of AB and AC. Therefore, we have AP equal to PB and AQ equal to QC. AP equal to PB, AQ equal to QC, because P and Q are the midpoints. Now let me consider the ratio AP by PB. This will be equal to 1, and the ratio AQ by QC also will be equal to 1. Therefore, I can write AP upon PB equal to AQ upon AC. Now in triangle ABC, we have AP by PB equal to AQ by AC. This implies PQ is parallel to BC. So hence we have proved the converse of midpoint theorem using the converse of Tayl's theorem. That's all for today's session. We shall continue the remaining part of questions of exercise 6.2 in the next session. Thank you. AB is parallel to PQ.